Okay, so last part of this super vector machine and also of the day. So let's see, okay, how to deal with nonlinear separations, okay? And this is made using kernels, which is something you can use with super vector machine, but then it can be used in many other applications. I think there is a kernel PLSDA. There are kernel classification. There are methods called potential functions, which are based on these kernels. So they are very, very powerful. We will try to have a look in a very easy way, in a graphical way. Okay? So don't be scared. First, okay, let's say we have two classes like this, okay? I don't know, this is kind of, have you ever been in Rome? Yes or no? Yeah, you know, we have Vatican City, okay, which is exactly inside Rome, okay? This is a kind of Vatican City inside Rome, so if you want to classify, of course you cannot classify the red class here with a linear separator, okay? So you need a nonlinear boundary. Plus, I didn't say this before, but if you are familiar a bit with classification and you know what is class modeling, like Synca, super vector machine can be also used as a class modeling method, so as a one class classifier, but this is another topic, okay? Yeah, they can do. And there is a nice paper of Brereton describing how to do that. Anyway, but this is another topic. So, here we need a nonlinear separation, okay? Nonlinear means that here we have two variables, okay? This is our linear combination, okay? We say that if the linear combination is higher than 0, then we predict the sample as red in class 1. But as you can see, okay, we can make this combination adding nonlinear terms, okay? And we can put all the nonlinear terms we prefer, okay? So, you can also write this with a different notation, okay? F1 is just, okay, the first term, F2 is the second term, F3 is the third term, okay? Some of these terms are linear, some are the interaction between variables, some are the squares of the variables, okay? And you can do, I mean, you can write it in a different way, but it's always the same. Now, the problem is that how do we define how many terms we have here? I don't know, okay? And this can be, both in a computational point of view, very expensive. And this can really bring you to overfitting, okay? So, there is another way to try to calculate nonlinear boundaries, okay? Instead of doing this stuff, which is by means of kernels, okay? So, what is a kernel? It's a way to look at samples on the basis of distances they have in between them, okay? So, let's start with a very simple example, okay? So, with kernels, okay, we define like new features, new variables, okay? And to define these new variables, okay, we need some landmarks, so some benchmark points, okay? So let's say in our very simple example, here we have two variables, so a b-dimensional space, okay? Let's say, by means of kernels, we define, or better, let's say that we define 3 landmarks, first one, the second one, and the third one. Okay? Now these are random. Then we will see what these landmarks are and how can they be defined. Okay? But now let's stay on this simple example. So we define 3 landmarks in our space. Okay? By means of these 3 landmarks, we will define 3 new features. Okay? 1 for each landmark. How? Okay. Let's take one sample. Okay? And we define a new feature depending on the proximity, so the distance, the similarity of the sample with respect to each landmark. Okay? And we define this proximity or similarity in this way. Okay? So, this is the first new feature we have, F1, for a given sample. Okay? Which is the similarity of this sample to what? To the first landmark. Okay? Then we can do the same for the second and for the third. Okay? These are independent. Okay. What do I mean with similarity? Is a measure of the proximity of a sample to the landmark. Okay? So, let's say, okay. Let's say we have a sample A here and a sample B here. Okay? Which of the two samples is more similar to the landmark number 1? A. Okay? So, this sample will have higher similarity. Okay, and this will be the feature, the new variable of our data set. Okay? So we dismiss variable number 1 and variables number 2. And we use this new feature. Okay? When looking at landmark number 2, both samples will have similarity, right? Because they have a similar distance. Okay? Now, this similarity is a number. Okay? So I need a measure for that. I can do even here in many ways, but the most common is with this stuff, which should remind you more or less something like kind of Gaussian stuff. Okay. Where this is a kernel parameter we have to fix. Okay, now things get a little bit complicated. So this is something we have to fix to the side, and we will see which is then the consequence of this kernel parameter, okay, on a super vector machine. And this is just the distance, the Euclidean distance, okay, is the length of the norm of the difference between my sample and the landmark, okay? So, if my sample, let's see if my sample, let's say this is sample number C, okay, which corresponds to my landmark, okay, which is the value of the similarity for this sample with respect to landmark number 1. 1? You said 1? Okay. Because this term is 0. Okay? And so this will be 1. Okay? While this sample will have a lower similarity, because this term will be higher. Okay? This is the, how does it work? Okay? This is it's called a Gaussian kernel. Okay? And this is, as we say, the distance, the squared Euclidean distance between the given sample and the landmark. And I do this for the first landmark, but then I can do that for the second one, the third one, and so on. And this will be my new features. So for every given sample, I will have similarity with respect to the first landmark, to the second one, to the third one, and so on. Okay, these are my new features. Okay, this is exactly what we were saying. Okay, I can do this with respect to the first landmark, the second one, the third one, and so on. Okay? Again, this is exactly the same, okay? I'm not too fast because it's exactly what we said before, okay? This is, again, the similarity, okay, between a given sample and landmark number 1, for example, okay? And we say that if a sample and the landmark are very, very close, the similarity is close to 1, as you see, okay? Okay, because this is low. If the sample is far from the landmark, okay, then this distance is high, okay, and so the similarity, all this term, or the Gaussian kernel, will be low, okay, and goes to 0. Okay? Now, if you want to see it in a, let's say, graphical point of view, and see which is the effect of sigma, but if you remember Gaussian distribution, okay, you probably already understood that. Okay, here you are. Okay, for example, this is a graphical example. So what happens? Okay, here I have just a generic, okay, space with two variables. I have a landmark, okay, in this position, 4 and 7, so I'm here. And this is, okay, the similarity with respect to this landmark in the space, okay? And you see the similarity is equal to 1, okay, in the landmark, and then it decreases if I go far from the landmark. Okay? And of course I get this plot with this value of sigma. But as I said to you, we can change sigma. Okay? And which is the effect of changing sigma is this one. As for Gaussian distributions. Okay? If sigma is high, how do you say? You reduce, okay, the effect of the kernel, and so you get more smoothed similarity functions, okay, like this one. If sigma is low, so if you decrease sigma, then you get landmarks, I mean similarity functions with respect to one landmark, like this one, okay? Can you see the same landmark, okay, the two different similarity functions. Can you see that, the difference? Okay, it's the same as when you do, if you look this in a univariate way, it's just having a Gaussian distribution like this, and if you reduce sigma, then your Gaussian distribution becomes like this, right? Okay, it's the same. But here we have to define what is sigma. Okay? And so you can do it more specific or, let's say, more generic. Okay? We can start saying that the lower sigma is, the higher the probability you overfit your data. Okay? And that's all. Now, let's say that in our stupid example, we use these free landmarks. Okay? So, for any given sample, we calculate the free Gaussian kernels with respect to landmark number 1, 2, and 3. And these will constitute our new variables. Okay? And then we can apply super vector machine on these new variables. Okay? So if you look here, I have my data set. I don't know. Can be a spectral data set, 100 sample, 500 wavelengths. Okay? Now, how many landmarks you want to use? Give me a number. Small one. 10. Okay? Let's say we define 10 landmarks. Then we will see how. Okay? But let's say we define 10 landmarks. Okay? So for each sample, I get the 10 similarity function with respect to these landmarks. So this data set now has these sides. And each of these, each of these value is that those similarity function. Okay? F of a given sample for a given landmark. Okay? In our example, let's say we have 3 landmarks, so we have 3 new features. We do super vector machine on these new features. Okay? And we use exactly the same approach. Then we classify our sample as reg. Okay? If the linear combination of these new features, not the original variables, but these new features, is higher than 0. Okay? It's exactly the same. But you don't have the original variables, you have these new features, okay? Which are the similarity with respect to these landmarks. Okay? Imagine, by chance, that these coefficients are minus 0.5 for the intercept. Okay? This is a super vector machine. Okay? So it SVM found these to be the coefficients that maximize the margin between the classes in this new space. Okay? And the coefficients are minus 0.5, 1, 1, and 0. Okay? What does it mean? Now, I get a new sample. Okay? This one. This sample will have, for the first feature, so the similarity with respect to the first landmark will be very high, close to 1, right? The similarity with respect to landmark 2 and 3 will be close to 0, right? When we do the linear combination, what do we will get as linear combination? Let's see if at 3 o'clock you can do this. Is minus 0.5 plus 1 times 1 plus 0 plus 0. Okay? Right? So the linear combination is 0.5, which is higher than 0. Okay? So I will predict this sample to be in the red class. Okay? Now I get a new sample, which is here. Okay? Same approach. The similarity with respect to all the landmarks, let's say it will be very low, close to 0. Okay? So the linear combination here in this case will be equal to minus 0.5, right? So I will predict this sample as not in the red class, but let's say in the blue class, in the other class, right? Okay. So the consequence is that all points close to these two landmarks will be in the red class, and the points which are far from these two landmarks will be in the other class, right? So you will have something like this, which is a non-linear separations between the two classes. Okay? Yeah? This is just a stupid example with 3 landmarks, 2 variables, and these coefficients, okay? But this is how does it work. A sample which is here will be in the red class because the similarity with respect to these two will be not exactly 1, but will be a little bit positive, okay? And when you do the linear combination, this will be higher than 0, and so it will be in this class. A sample which is here will have the first 2 features, the similarity with respect to these 2 landmarks equal to 0. The similarity with respect to this one is equal to 1, but the coefficient is 0. Okay, so the linear combination will be minus 0.5, so it will be in the blue class. So you will get a separation like this, okay, which is not linear. Okay, and this is how does it work. Yeah? Okay. It took a while for me to understand this stuff. Okay, so
why do you choose this value? You decided to go to
just an example.
Okay.
Just to, I mean, a simple example, okay? Just to understand what's going on. Mm-hmm. It just, kernels means that you define new features which are based on the distances or similarities with respect to some landmarks. And then you use these features as variables for a supervector machine. And then you use this exactly the same approach as we saw before. Okay, so the supervector machines tries to find the coefficient vector which will maximize the margin between the two classes, but in this new space defined by these new features. Okay? And the conclusion is that you get a nonlinear separation. Okay? Now, here, this is a stupid example with 3 landmarks. I decided to put in these points, but okay, how do we define the landmarks? Which means the dimension of this new space, okay? So, the landmarks are all your training samples. Okay? All the training samples are used as landmarks, as reference. So, okay, it makes sense. This is the reference for you to classify. Okay? So, let's say we have 500 training samples. Okay? All these training samples are landmarks. Okay? So when I get a new sample, I get the similarity of this new sample with respect to all the training samples, and these will be all the features of my of the samples I want to predict. Okay? So if I have 500 training samples, okay, I get how many features? How many new features? 500. Okay? And I will use those features, okay, to then calculate super vector machines. Okay? So for example, this is my generic sample. Okay, let's say it's a spectra. You are all familiar with spectra. Okay? So it's a Raman spectra. So this is a signal. Okay, you have measured in all the points. Okay? But when you use kernels, then you calculate the distance, the similarity, okay, on the basis, for example, of a Gaussian kernel with respect to all the training samples. So the new features will be similarity with respect to the first training sample, to the second training sample, to the third training sample, and so on, until the last training sample. So how many features now you have? 500, if you have 500 training samples, okay? And then you use this, okay, data to do super vector machine or whatever you want. Okay? Do you remember this from this morning? Okay, this is the linear combination of super vector machine, and this is the optimization function. Okay? With coefficients and the cost. But now, okay, the linear combination, okay, is not referred to the original data, but to these new features. These are the coefficients, and these are the new features we got from the kernels. Okay? And this is the linear combination. I have the coefficients associated to all these new features, okay? And if I have n training samples, I will have n features, okay? You remember this term? This was the regularization term, okay? Now, it's the same, okay, these are the coefficients, but how many coefficients I have? N, because I have n features, as many as the number of training samples. Okay? But in this way, things get more complicated. Now we have, in the next hour we will have some practical examples. But if you have a nonlinear discrimination, you can use it to find the real nonlinear separation between the classes. Okay? This is how does it work. I mean, if you go back and think about it, it's not so, I don't know, complicated. Okay? You have just to think about this as similarities. Okay?
Davide?
Yeah.
So then for prediction,
Yeah.
you need the original data, the training data to calculate
Mm-hmm.
with the new samples
Yeah, of course.
to calculate. Okay.
Yeah.
And then this you predict that thing. Okay.
Yeah. I mean, you get a new sample, you calculate all the similarities, these are the new variables, the new features, and then you use these in the model.
Mm-hmm.
Yeah.
Okay.
Now, in a practical point of view, okay, when you do super vector machines, you have to choose C. Okay, we have to put the number here. And also, if you use not linear super vector machine, you have to define this sigma. Okay? How do we do that? I mean, as we do in to choose the number of Latent variables in PLSDA, to choose the number of trees, okay, for random forest, we do in cross-validation, a trial and error procedure. We can change C we can change sigma and see in cross validation which is the best option. Okay, but we can start saying this thing. Okay, you already have seen this plot somehow, somewhere. Yeah? So you have, when you define, when you tune a model, so you select the number of latent variables or whatever, okay, you choose the model complexity, okay? This should be the optimal solution. If the model complexity is too high, then you reduce the variance, but you augment the variance. While if the model complexity is too low, then you reduce the variance, but you have a high bias. Okay? So, in a practical point of view, let's say you have two classes, okay, with a little bit of overlap, and this might be a good, reasonable, not linear discrimination, okay, which corresponds to this complexity. If you use, okay, a too complex model, then you may find this separation, that one, okay, which is overfitting, okay? This is not the actual real separation between the two classes, and you are over-describing your training samples. While if the model complexity is too low, then you underfit your data, okay, like in this case, okay? Now, which is the effect of C and sigma, okay, in this framework? If you remember, we already said that using a too small C value, okay, means going in this direction, okay? You want the margin to be too high, okay, and you probably have a too high bias, okay? While the opposite, if you use a large C value, okay, do you remember using a very high C means we have to reduce this stuff, and so we have to reduce the margin, which may lead you to overfitting. Okay, so this is the effect of changing the C, the cost, when you optimize a super vector machine. Okay? Large C overfitting, small c, let's say underfitting. Okay? And we have to find the correct trade-off. I mean, small c can be fine. I mean, if you have a perfect separation between two classes, small c can be. I'm not saying that you don't have never to use a small c value, okay? But it depends on case by case. But this is the effect of the cost value. Sigma, okay, is the opposite. So when you use a large sigma, okay, do you remember the effect is to have a very large Gaussian kernel? Okay, so large sigma can bring you to underfitting, but on the opposite, of course, small sigma, very small sigma, can bring you to overfitting. Okay? Honestly, between the two situations, I would prefer to stay here, okay, instead of overfitting. Anyway, this is the effect of sigma. Okay? Here things get more complicated because if you want to use it in a nonlinear way, we have two parameters to control. Okay? Few final slides, but then I want to go to the practical session so we can have more fun. Just to show you, but we will see it in a practical way. Okay, if we use linear super vector machine, this is a simple case where we have two classes, okay, blue and red class. I did two super vector machine models. This is based on a very low cost, and this is based on a very high cost value. Okay? And can you see how here the margin is smaller? I mean, here the separation is nice, okay? But can you see here the margin is smaller because the cost is higher, okay? This is the effect. So you have a lower margin. All these points are the support vectors. Can you see? All the blue samples, this is the blue space, the red space. All the blue samples on the margin or behind the margin, okay, are the support vectors. All the red samples on the margin or behind the margin are support vectors. Okay? Here is when I reduce the cost. Okay? The number of support vector here is higher, of course, because the margin is higher. Okay? This is the effect, okay, of changing C. While this gets more complicated now, this is what happens when you use, this is, I guess, is the same data set as before, okay? But now I'm trying to use not linear support vector machine. So I'm using a kernel, okay? So instead of using two variables, okay, here I'm using all the features which are the training samples. And you have 4 cases, okay, where I changed the cost and the sigma, okay? Let's try to see what happens when we fix the cost and we change sigma, okay? Here you have cost equal to 1 and a very low sigma, okay? And can you see this black is the separation, is the boundary between the two classes, which is not linear. This is the margin. I mean, of course, this is very different with respect to what we have seen before, okay? This is the margin, and these are the support vector, okay? Can you see the effect of sigma? When do you remember, if we decrease sigma, we augment the probability of overfitting, okay? Here you have this separation boundary, okay? These are the two margins, and these things are quite different with a smaller sigma, and probably we are overfitting the data, okay?